Hello. So today we will be talking about the op-amps. This is from chapter 8 in the book. We have skipped it earlier, but now it's the time to come back to it and discuss the op-amps. Op-amps refers to operational amplifiers. We can utilize them to do multiple functions that we want, and they are quite useful. So the op-amps, and this has this symbol. So this is the operational amplifier. And this is chapter 8. Okay, so the operational amplifier, we typically have this symbol for it. It has two inputs, Vn positive and Vn negative, or double N, and we have either one output or two outputs. So the positive one, we call it, this is non-inverting. And this is the negative side, is called the inverting terminal or input sides. Okay, we give it this symbol, but what is inside this operational amplifier? It's, you can see as it has two inputs and one output. So whose amplifier this reminds you of? So for sure, there is a differential amplifier inside this operational amplifier, but typically it's not a one stage. It has multiple stages, either two or more, in order to get higher gain, because one of the main requirements or the main features of the operational amplifier that it should have large gain. So it should have very large or high gain. Large, high gain, so more than let's say 60 dB gain we should have. We also, so, and we give this symbol of the gain A0, or the open loop gain. Now when we will see that we are going to close the feedback or have a feedback from the output back to the input, we will call it a closed loop gain. So we need to differentiate between them. So when it's like this, there is no connection from the output back to the input, then we are calling it an open loop gain. When we are going to have a connection or a feedback from the output back to the input side, then it's going to be a closed loop gain, and there is a difference between them. Okay. So this is one of the main characteristics. For it should have also high input impedance. And very low or almost zero output impedance. Why this? If you remember, or if you think of like this op-amp is not alone, but it's connected to some other stages. So this is first stage, is connected to a second stage, and then there is a third stage, just for example. Okay, so this is V1N, this is V out 1, this is V out 2, and this is V out 3. Okay, there is obviously going to be a feedbacks around each one of them, but just for the sake of simplicity, we want to understand why we want high input impedance and high input impedance and low output impedance, because I want more for example, if I discuss this second stage, I wanted to have very large input impedance. So if you think of a voltage divider, this is the output impedance of the first one, R out 1, and assume that there is an input impedance of this Rn2. So I want, and here I have the V output 1. I want most of the output to come and be applied at the input of the second stage here. So that's why it's kind of a voltage divider. So I want to, as an input, to grab all the signal from my previous stage and take it to me. On the other hand, why the output impedance should be low? For the same reason, so that I don't keep the output with me, I give it to the stage that is coming following me. If you thinking of it of a voltage divider will make it very much simplified for you. So we want to give all the output to the next stage. That's why we need to have lower output impedance and large input impedance. Okay, so the relation between this V output and V input is basically V out equals to A0. Oh, it's not right. A0 multiplied with the Vn positive minus the V input negative. So this is the relation between the input and the output of the operational amplifier. And again, A0 is the open loop gain of the amplifier. So in order to think of it in a different way, if we say that Vn positive minus Vn negative equals to V out divided by A0. And we said that A0 is very, very large value. This makes sure that we are going to have, since it's a very large value, this term here will be what? Very, very small. Therefore, we can assume that V input positive almost equal to V input negative. Again, assuming A0 is very high. Okay, I mean, in the ideal amplifier, A0 approaches infinity, like infinite gain, let's say. I mean, ideally, there is no infinity, no amplifier with infinite gain, but for the ideal op-amp case. So we want it to be as large as possible. Okay, now what does this mean that V input positive equal almost to V input negative? Are they shorted with each other? The answer is no, they are not shorted with each other, but they have almost the same polarity without being shorted to each other. Okay, so that is something very important for us for deriving the relationship or the closed loop behavior of the differential amplifiers. Okay, let's see what we want to say next. Let's take a simple example. If I have this circuit, and the V input is applied here, and it has an open loop gain of A0, and this is the V output. So I want to know, this is Vn1 and this is Vn2. So my relation is that V out still equals to A0 multiplied with a Vn1 minus Vn2. But how Vn2 is related to V out? We can see that they are shorted with each other. So V out equals to Vn2. Now, if I just replace Vn2 here in the original equation with the V out, so we will have V out equals to A0 times Vn, because Vn1 equals to Vn minus V out. So now I just rearrange it, take this to the other side. I will have V out times 1 plus A0 equals to A0 times Vn. So V out over Vn equals to A0 divided by 1 plus A0. And when A0 is very, very large, this term approaches to 1. And so this circuit is basically acting as a voltage buffer, as you can see. So we just shorting the output back to the negative terminal gives you a voltage buffer. So we are having almost the output equal to the input. So that's a very useful circuit for us in some cases. Okay. Now we want to discuss furthermore examples or type of the circuits. We have the non-inverting amplifiers. Okay. So if we look at this topology, we have the positive, the negative terminal, and we have here the Vn. And this is R1, this is R2, and we have V out, open loop gain of A0. This is Vn1 and this is Vn2. Now this amplifier is called non-inverting because the input is applied on the positive or the non-inverting terminal of the amplifier. So when the input is applied at the non-inverting terminal, we call it a non-inverting amplifier. And we will see that the inverting amplifier is basically when the input is applied at the inverting terminal of the amplifier. So this is the naming convention that we are using. So we want to derive the gain of this. Now this gain is going to be called a closed loop gain. Why? Because now there is a feedback, and that's the same thing which we just did here. So what we found here is basically this is also a closed loop gain. Just forgot to mention. So the open loop gain remains here to be A0. Now we want to find the closed loop gain. And the closed loop gain here is basically, we want to derive it with the same relation that V out equals to A0 times Vn1 minus Vn2. Now I just want to find out how Vn1 is equal to Vn and Vn2 is equal to what? How it is related to the V out. So it is basically related to the V out with the voltage divider here. So it is R out, R2 divided by R1 plus R2 times V out. This is similar thing to what we were doing in the feedback chapter to find the relationship between the output and the feedback path. So here, this is somehow the K factor that we, or the beta factor that we used to find there. So if you want to apply that knowledge which you studied earlier in the feedback, it is still valid here and you can definitely apply it. Yes, so let's plug it in here. So we have V out equals A0 times Vn minus R2 over R1 plus R2 times V out. So rearrange the things, we will get that basically V out times 1 plus R2 over R1 plus R2 times A0 equals to H0 times Vn, and therefore V out over Vn equals to A0 over 1 plus R2 over R1 plus R2 times A0. Now, when this A0 approaches infinity, we can simplify this. So this term will be much greater than 1. And therefore, I can just cancel those with each other, and we will have V out over Vn equals to R1 over R2 plus 1. You just flip it, and after simplifying it, it will become just R1 over R2 plus 1. So this is the non-inverting amplifier gain, assuming an infinite open loop gain. I mean, even still, this relation is a correct relation, just we are looking for simplicity when we assume an ideal amplifier with an infinite open loop gain. So again, R1 over R2 plus 1. Now you can see that the closed loop gain is completely dependent on the feedback factors or the components that forming the feedback. So here we have dependent on the ratio between the resistors R1 and R2. And in the circuit design, we typically like this to have gains that dependent on a ratio of resistors or a ratio of capacitors. Why? Because those are very useful to avoid variations when manufacturing the devices. Those small variations in the width or length of the transistor can change the GM, and then they can change the gain. If you remember the gains that they used to depend on the GM, while having a gain dependent on the ratio of those components. So if R1 increases by, let's say, 2%, R2 will also be increasing by 2%, but the ratio between them will still remains the same. And that's the good thing. So the gain will not be affected by changes in the manufacturing process. Now, let's talk about the inverting amplifier now. So what do you expect here? That the input will be applied at the negative terminal of the amplifier. So we will have it here. We have here just the V out, and has an open loop gain of A0. Okay, so again, A0 is very large. When A0 is very large, then we assume that Vn1 almost equal or equal to Vn2. But now you can see this is Vn, let's say 1, and this is Vn2. Okay, so you can see that Vn1 is shorted, and therefore what happens to Vn2? Vn2 at this node X is basically called a virtually ground. So node X is a virtual ground, means it has a zero potential, but it's not actually shorted to ground. Similar concept to what we discussed in the differential amplifier before. Therefore, now what's going to happen? The current here is going to be equal, this current I1, let's call it I1, will equal to Vn divided by R2. And this same I1 will continue and go through R1. Why nothing goes into here? Why nothing comes here? Why? Because you remember this is the going to the gate of, if we remember, it's go to the different gate of the differential amplifier. So nothing goes there. So all the current will go into R1. Okay, so now V out will equal, because the current direction is different, minus R1 times I1. So it will become minus R1 times Vn over R2. And therefore V out over Vn will equal minus R1 over R2. So this is the closed loop gain. Again, it's a depending on the ratio of the resistance, and it has a negative sign because it's an inverting amplifier. Okay, so this is the gain of the inverting amplifier. It's very important for us when we talk about inverting amplifier to consider node X as a virtually ground and use this current relation. So the same current that's coming from the input side will continue in the feedback and forming the V out with the feedback resistor. Okay, so that is important thing. Now, one more important circuit that we want to discuss is called the integrator. Here, basically, it's very useful circuit that we also form it using the op amps. And basically, it has of the similar idea. It's an inverting. However, in the feedback, I don't have a resistor, we having a capacitor. So this is C and this is R. So now again, Vn1 will also equal to Vn2, and therefore this node X is acting as a virtual ground. And we will have the same, the current here, I will continue here. And I will equal Vn divided by R. Now V out will equal 1 over C times S multiplied with this current I. So V out over Vn will equal to 1 over Cs times Vn, sorry, the Vn here, okay. Just 1 over R. So the gain will be V out over Vn will equal to 1 over C S times R. So this is the closed loop gain of the integrator. Okay, now why it's called integrator? Because output is basically the integration of the input on the feedback capacitor C. Now, if we want to look at it from a time domain point of view, rather than using the Laplace here with the 1 over Cs. So if we have V, basically N over R, which is the current, is equal to minus C1 times dV out over dt. So the current through a capacitor is equal to the integration of the voltage at that capacitor multiplied with the C, as you remember from before. And why the negative sign? Because the direction of the current is different according to the voltage. So now V out is going to equal, so in order to get rid from this derivative sign, we need to integrate both sides. So V out will equal minus 1 over RC times the integration of the Vn dt. That's why it's called the integrator. And it's very useful circuit. We will need it, or you can use it in multiple application. Now you can see here at DC, this has a sort of infinite gain. If you want to have it with a fixed value of a gain, you can place a resistor here, R2, in parallel with this capacitor, and we call it in this case a lossy integrator. And you can try to derive the functionality of this integrator, lossy integrator, by basically assuming now that you have a parallel combination in the feedback path formed with this capacitor and so 1 over CS in parallel with the R2 when you want to find this component here. So this will be replaced with 1 over CS in parallel with the R2. And that will help you to find, so you will have a fixed value of the gain for at the DC. Okay, so those are the main circuits that we wanted to discuss as a basic level. There are many other important circuits that you can develop from this. We can discuss further in the next classes, but I now want to show you some simulation examples. So let me share, I want to share my screen. Okay, I'm saving them. And now I want to share my screen from the other computer. Okay, so here this is a nice application that you can basically see how the behavior of the amplifiers. So let's take some examples. So what type of amplifier here? We have a non-inverting amplifier. Why? Because the input is being applied at the positive or the non-inverting terminal of the amplifier. So what do we expect the gain to be here? The gain is going to be 1 plus the ratio of R1 divided by R2. Here, both of them, R1 and R2, they are equal to 100K, which is going to give us a gain of 2. Okay, so let's see, are we getting a gain of 2 or no? Okay, so now our input is coming on the blue channel, and it has a level of, so each division of those squares, it's equal to 5 volt. So you can see that this is 5, the input blue, while the yellow one is a 2 division, which means it's 10. So we have a gain of 2. Now let's try to play with this gain. So if I make this to be, let's say 200K, so I'm going to gain a gain of 3. But now you can see that I start clipping at this part here. Why? Because my output should be 15, but my total supply voltage is basically 12 here, the supply voltage. So if I reduce my input range, so where I can change, I want to change the input and basically make it 1 volt. So now when I make my input 1 volt, let's change this division to as well 1 volt. Yeah. So maybe this is not 1 volt. So it's taking it, yeah, peak to peak value. So you can see that there is an amplification happening here with a gain of 3. Now, if I reduce this, make it, let's say 20. So here we cannot get a gain that is below 1, but we can get, I mean, 1 point something. So here 1.02, but the divisions, they are not the same. Let's make them the same. We should expect that they are almost equal to each other with the gain of 1. Okay, and you can see that they are non-inverting gain. So both the input and the output, they are, let's say, in phase of each other. There is no phase shift between them. Now, let's try to change this and have a different amplifier. So let's have an inverting amplifier. So the gain of the inverting amplifier is minus R1 over R2. So the ratio between those two, again, here they are equal to each other. So the gain is 1 minus 1. That's why you can see the phase shift. The amplitude remain the same, but there is a phase shift of 180 degree. Now, if I change this one and make it, let's say, 400 something. So the gain is again increasing and we can see clipping. I don't want it to go that much. Let's change it. And so basically when you give too much high gain, then the amplifier saturate, and that's why we see the clipping. Okay, here it did not change too much. I wanted, let's say 200. So we should get a gain of -2. Now, if this goes low, below 100, we should have like attenuation. So here should be much attenuated. Now you can see the yellow almost disappeared. Let's decrease the division of the yellow point, assuming that this is our oscilloscope. You can see that's very tiny signal that we are seeing here. So this is nice to see how these amplifiers behaving. Okay, and I also wanted to show you on the LT Spice how to simulate it. Just I want to share the audio of this. So let me share my screen again.
Now we're getting into our first topology is the inverting configuration. This is what it looks like. We are using the same op-amp part that we created in the last video, so we are still dealing with idealities. With the addition of just 2 resistors, this circuit becomes a closed loop with controllable gain. The power supply and the feedback are both tied to the inverting terminal, hence inverting configuration and negative feedback. Let's see if we can't figure out what the closed loop gain of the amplifier will be and then verify it with the simple simulation. To find the gain of a system, we take the output signal and divide it by the input signal. So first we need to get an expression for V in and V out in terms of the resistance. To do this, we'll perform nodal analysis on this node here. Since we are still working with the ideal op-amp that we built in the last video, we can make a few assumptions here. First is that V plus and V minus are equal to one another, and since V plus is physically tied to ground, the voltage seen here at this node is 0. So to perform nodal analysis, we're going to take the sum of the currents going into the node, which, so if we call this one I1, that current, which is equal to voltage divided by resistance, will be V1 or V in minus 0, so just V in divided by R1. Let's just make a little text of that. So we have I1 is equal to V in minus 0 divided by R1. And here we have, and since we know that this is 0 volts, and we know that current flows from high to low potential, the current going into this node is flowing from V out into this node. So we're going to have this current, I2, is going to be equal to V out minus 0 divided by R2. So we have I2 is equal to I2 is equal to, so V out minus 0 divided by R2. Now we know that the sum of currents flowing into the node is equal to the sum of the currents flowing out of the node. So we have I1 flowing in this direction, then we have I2 flowing in this direction, which means they're equal and opposite, which means that I1 is equal to the negative of I2. So we have I1 is equal to negative I2. And to put down one more equation, we have that the gain is equal to V out divided by V in. Well, it looks like we can already figure out what that gain is because we have an expression with V1 here, or V in here, and we have an expression with V out here. So if we set these two equal to each other, we get that the gain is equal to V in over R1 is equal to minus V out divided by R2. I guess I'll gotta move these. So if you rearrange these terms, which would just be multiplying both sides by R2 and then dividing both sides by Vn, you get that the gain, or Vn divided by V out, opposite, V out divided by Vn, is equal to negative R2 divided by R1. And that's the gain of this closed loop negative feedback inverting configuration. So let's sim it. So we first need to put some values here, and this is what's pretty cool about LT-Spice is, let's say you're doing a homework problem and they only give you one value for R1, and you have to compute this value. You actually don't have to do the math, which would be a simple division, but you can set up this as a parameter and have it step through until it finds the correct value that you need. So let's say we have a resistance up here of 10K, and we want our gain to be 10. In order to get a gain of 10, we would have to set this to 1K. So let's first verify it, then I'll put in some wonky value here, and then we'll set up this as a parameter and find the exact value of R1 that gives us that output. Okay, so let's sim this. We've got V1 is equal to 1, so our output, what we should see is negative 10 volts all the way across, and let's see if that's true. So we'll run it, we'll perform a transient analysis. Let's do something really short, 0.1 milli. Probe the output, and there we go. We see it exactly negative 10 volts. And I mean, I'm cheating just a little bit by placing V1 as 1, because if you wanted to find the gain, what you would really do is you'd perform an algebraic expression up here at the top of the plot plane. So what I did was I right-clicked on V out, and it's going to give you this text box here. And so the gain is actually the voltage out divided by the voltage in. So you're actually going to have to type in that expression. So you want to find V of V in. So it's V out divided by V in, right? And because it's 1, it's going to be the same. But most of the time you're not going to have an easy voltage here. So that's how you would do it, like if you're doing a homework problem or if you're doing a real op-amp analysis and you want to find the gain.